Welcome back. In this lecture, we will continue the analysis of 1D wave equation. Let me recall what we did last time. So, we were discussing the initial value problem or Cauchy problem for the one dimensional wave equation. Okay, let me write it utt minus c square uxx equal to 0. So, it is homogeneous wave equation. So, right hand side is 0. So, this is for x in the real line and t positive. And we are prescribing initial conditions at t equal to 0. So, namely ux 0 equal to u 0 x and u t, the first derivative of u with respect to t at t equal to 0 is equal to u 1 x. So, here u 0 and u 1 are arbitrary given functions. U 0 is a C2 function and u 1 is a C1 function, and the solution is given by the D'Alembert's formula. Recall this. So, we derived this in the previous class. So, the solution is given by this D'Alembert's formula. So, let me write it once again. Equal to half u 0 x plus c t plus u 0 x minus c t plus 1 by 2 c integral x minus c t to x plus c t u 1 eta d eta. So, this is D'Alembert's formula and so just we derived this previous time. So, it is not necessary that, so this is again x is in R. So, we are providing the initial conditions at t equal to 0. So, let me denote this by 1 and this D'Alembert's formula. So, you just remember this D'Alembert's formula, which is used repeatedly. So, it is not necessary that we prescribe the initial conditions at t equal to 0. So, we can prescribe them on any line t equal to t 0. So, let me write it the another problem. Okay, so, this is, so let me write it again, it is homogeneous wave equation. So, let me use a different function here. Equation is same, but now we are going to prescribe the initial conditions at some other t equal to t 0. So, this is again x is in R and now I am taking t 0. So, previously t 0 was 0, but now I can take any t0 arbitrary real number. So, and I prescribe the initial conditions at time t equal to 0. So, that is my initial time. Okay. So, I use the same u0 xt. So, u1x. The wave equation has many nice invariant properties. So, one of them is translation invariant, which is easy to verify. So, if you change t to t minus t0, the wave equation does not change, and exploiting this property we can write down the solution of 3. Okay. The solution of 3 is given by, very simple to verify, u of x t is equal to small u of x. Now, just you are translating. So, t minus t0 and t is bigger than or equal to t, where small u is solution of the problem 1 which is given by the D'Alembert's formula. So, this capital U is also given by the D'Alembert's formula. Only thing is you have to change t to t minus t naught, that is all. Okay. So, this we are going to use little later, and more generally. So, that is just a remark. So, even for this solution of the problem 3 is neatly given by the D'Alembert's formula with t replaced by t minus t 0, that is all. There is not much difference there. More generally, so this is just a remark, initial data can be prescribed on any non-characteristic line curve, on any non-characteristic curve t equal to pi x. But then there will be some conditions on phi in order to show that the solution exists, and certainly solution is not given in any closed form. So, this existence has to be proved by using some fixed point arguments. Okay. So, the details you can find it in our recently published PDE book. Okay. So, so we next use D'Alembert's formula to prove a simple estimate on the solution. Okay. So, assume that the initial functions u0 and u1, assume u0 and u1 are bounded functions. say u1 u0 x absolute value and also u1 x absolute value, both are less than or equal to m for all x in R. Okay. Then you go back to the D'Alembert's formula. So, again I just equation number 2, D'Alembert's formula. So, now you take absolute value on both the sides, and by our assumption this u0 is bounded by m. So, you get 2 m here, there is a half here. So, you get m, and again in the integral side you take the absolute value, and that is also bounded by m, and then you integrate the constant, you get 2 c t, again you get 2 c 2 c cancels, and what we get is, so this is a very simple estimate. I just write it. Then for any t positive, so this is just direct consequence of the D'Alembert's formula. Then for any t positive, we have mod of u x t this I take less than or equal to m times 1 plus t for all x in R and t less than or equal to t. So, there is a t here. Okay. So, what this estimate says is at any positive time t, u is also a bounded function of x, okay. But it may not be bounded function of t as t grows. So, this right hand side also goes, but this is useful. Generally such estimates are useful in establishing uniqueness and continuous dependence on the initial data. So, in fact, this if you replace m by sup u0 and sup u1, you see that. Okay. So, if you change u0 and u1 little bit, so the corresponding solution also changes very slightly, and that is continuous dependence on the initial data. Okay. So, this is so in case c is not a constant, then we do not have D'Alembert's formula. In that case, such deriving such estimates for solutions are very useful in establishing uniqueness and continuous dependence of solutions. A more physically relevant, so this is, you can say it is sup norm. Okay. So, this estimate is in sup norm, because we are taking estimate in sup norm. We are taking supremum over x in R. A more physically relevant norm is the energy norm. So, let me briefly describe that. Okay. And these are very useful in studying general hyperbolic equations, not only second order, but even higher orders and also systems. Okay. So, this is the this energy is the sum of kinetic energy and potential energy. So, this is total energy. So, this is defined by at time t. Okay, so, just half integral over minus infinity to infinity u sub t x t square plus c square u x square x t, and you integrate with respect to x. Okay, so, this is so the first term is kinetic energy and second term is the potential energy. So, sum of two energies. An integration by parts. So, let me just show you heuristically. So, provided this integral is finite. Okay, if integral is infinite, that does not make sense. So, for the time being, just assume that the integral is finite. Let me show you that this E t is constant. That means, it does not depend on t. Okay. So, for that, what we should do? We should consider its derivative with respect to t and show that that is 0. So, again formally, so assume that we can take the derivative inside the integral sign, and you see that so this is just nothing but minus infinity to infinity. The first term gives me u t u t t. So, I differentiate the first term with respect to t. So, that 2 goes away. So, just you have u t t, okay, plus the second term c square u x t. So, I am differentiating with respect to t. So, that is what I get. Okay. These are just heuristic arguments. We will make remark at the end of this derivation. And now, this one, okay, you can write it as this is equal to, let me write it here, d by dx of u t u x. So, if I do that, one term I get is this term, and now there is another term by product rule. So, that I have to remove it. What is that term? That is precisely u t u x x. Okay. And remember, we are integrating. So, this is d by dx term. So, I should just evaluate the limit of this at plus or minus infinity, evaluate at x equal to plus or minus infinity. So, that and you have to take the limit and assume they are 0. Okay. Assume equal to 0. So, they will not contribute anything to the integral. So, what I get is simply minus infinity to infinity. So, there is u t common here, there is u t here, there is u t here. So, u t t minus c square u x x dx. Okay. But this is, since u is solution of the wave equation, homogeneous wave equation, this is just 0. So, the whole thing is 0. So, that proves E t is a constant. Okay. So, this is a conservative system that can be expected because the equation is derived by using Newton's second law, and most of the equation derived by Newton's second law are conservative equations. So, the total energy is conserved. Okay. So, in general, when in the study of general hyperbolic equations, one considers such norms and tries to prove existence, uniqueness and other properties. So, because there are no explicit formulas for the solution. Okay. So, that is in the present case. So, we have again the advantage of the D'Alembert's formula. So, from the D'Alembert's formula, so this is an exercise for you. So, it is a long calculation. So, you have to do several okay, express this energy, namely this u t square x t plus c square u x square x t in terms of u 0 and u 1. Okay. So, that is in terms of the initial energy, because at t equal to 0, u 0 u x, for example, u x will be u 0 prime and u t will be u 1. Okay. So, you can express, because we have the explicit formula given by D'Alembert's formula, okay, and verify that it is a constant. But this advantage of an explicit formula is missing when the coefficients are variables or higher order equations. So, one has to deal with the energy directly. Okay. So, with this remark, just to move on. Okay. So, we will next discuss. So far we have discussed only the homogeneous wave equation, and now we will discuss inhomogeneous equation, and surprisingly even a formula for the solution of the inhomogeneous equation can be reduced to the solution of a homogeneous equation. Okay. And this is known as Duhamel's principle, okay, an important tool not only for the wave equation, but for many evolution equations. We will see even for the heat equation this principle can be applied. Okay. Very useful tool. Okay. So, let me just describe that Duhamel's principle. So, in fact, even for first order equation, not when you solve inhomogeneous equations, you are using Duhamel's principle in some form, okay, though you might not have noticed it, but it is hidden there. Okay. So, what is the problem? So, this again wave equation. So, instead of 0, now we have a forcing term. So, also inhomogeneous term is called forcing term. So, of course, that will certainly affect the solution. So, let us see how that. So, again x is in R. So, we are and T positive and initial conditions. Okay. So, that is let me write U 1 x. So, let me denote it by equation 4. Okay. So, obviously, some continuity assumptions should be put on f. So, let us first derive the formula and then we will see what conditions we should put on f instead of stating in the beginning itself. So, once you see the formula, we will know what condition to put on f, so that we will get again a C2 function, that is important. Okay. So, as usual this u0 is a C2 function and u1 is a C1 function. So, that is always there, because even when f is 0, that we need to assume. Okay. So, by linearity, so we consider two two similar problems. So, let me write it. So, this is homogeneous wave equation, and I take the initial conditions as V x 0 equal to u 0 x and V t 0 equal to u 1 x. Okay. So, let me call it phi. Okay. So, let me not repeat where is x and where is t. Okay. So, that is understood now. Okay. And another problem, now I take the inhomogeneous equation. So, W T T minus C square W x x f x t, and now sorry for that, not used W x 0 is 0 and W t x 0 is 0. 6. Okay. Of course, this problem 5 we already solved this, and the V is given by the D'Alembert's formula. So, there is no problem with that. Okay. That is no problem. So, but we have not done this one. So, we have by linearity. So, that is an important observation. So, then the solution u of problem 4 is sum of p and w. Okay. So, linearity plays a crucial role here and you can easily verify that the solution u of problem 4 is given as sum of solution of problem 5 and solution of problem 6. Okay. So, problem 5, as I said, so it is already done there. So, we have the solution in the given by the D'Alembert's formula. So, what remains to do with this problem 6? So, with this reduction, it is sufficient to assume that the initial conditions are 0. So, that is homogeneous initial conditions, only there is inhomogeneous term in the equation, okay. And this is solved by the Duhamel's principle. Okay. And so, to solve 6, we convert that into an initial value problem. Okay. So, that is the idea of Duhamel's principle. Okay. So, consider now inhomogeneous equation, homogeneous equation c square u x x equal to 0 x in R, but I take t bigger than s. What is s? In a minute I will tell you. And now I prescribe the initial conditions at time t equal to s, not 0, but at s. So, this I made remark in the beginning itself. So, we can x, and this you provide it by x. X in R. Okay. So, the inhomogeneous term, if you look at it, inhomogeneous term f appears as initial conditions for this problem. Okay. So, here s is bigger than or equal to 0 is fixed, but arbitrary. Okay. So, as we change s, so the problem changes and the capital U also changes. So, capital U in principle is a function of x, t and s orbit. So, by D'Alembert's formula, we have u of x t, okay, just to stress the dependence on s, because it also depends on s. So, we write this as yes. Okay. Just that is to just indicate capital U also depends on s. Okay. So, if you again look at the D'Alembert's formula, the u is 0. So, this will not contribute to anything. So, only the first derivative is given, and so and that is given by the integral of that initial condition. And now, we have to replace t by t minus s, remember that. So, okay. So, x minus c t minus s x plus c t minus s, sorry for that, f of eta s d eta. Okay. D eta. Okay. So, we will complete the solution of problem 6 in our next class. Okay. So, we will just remember this one and we will continue this in the next class. Thank you.